Hello everyone. Today, we'll be discussing flash memories, NOR and NAND architecture. Flash memory is an integral part of modern digital devices, enabling everything from portable storage solutions to fast system boot processes. Let's dive in to understand its fundamentals, architecture, applications, and limitations. Flash memory is a type of non-volatile storage that retains data even when the power is turned off. It is widely used in devices like USB drives, SSDs, and memory cards. This technology was invented in 1984 by Dr. Fujio Masuoka at Toshiba Corporation. NOR Flash introduced commercially by Intel in 1988 and NAND Flash following in 1989. It has since become the backbone of data storage, powering everything from personal gadgets to enterprise systems. Flash memory's versatility lies in its ability to store data in a compact, efficient design. Let's break down the structure and functionality of a basic flash memory cell. Memory cell structure. At the heart of flash memory is the memory cell, which consists of a floating gate transistor. These cells are arranged in a grid or array, allowing large amounts of data to be stored on a single chip. The floating gate is electrically isolated, enabling it to retain charge for a long time even without power. This isolation is what makes flash memory non-volatile. Data storage types. Data storage in flash memory comes in two main types. Single-level cells, SLC. These cells store one bit of data by switching between two charge states, representing a binary 0 or 1. This makes them fast and reliable, but they have lower storage density. Multi-level cells, MLC. In contrast, MLCs can store multiple bits per cell by distinguishing between several charge levels in the floating gate. While this increases storage density and reduces cost per bit, it may result in slower write speeds and reduced durability due to the complexity of charge differentiation. As shown in the diagram, each memory cell has a floating gate that holds the electrical charge. The charge level determines the data stored in the cell, allowing either a single bit or multiple bits depending on the architecture. This fundamental design, combining a floating gate transistor and scalable charge levels, forms the basis of flash memory, catering to diverse applications from reliable SLC storage to high-density MLC solutions. Flash memory chips rely on an ingenious architectural design to store data efficiently and reliably. Let's break down how this is achieved. Floating gate MOSFETs. At the heart of flash memory is the floating gate MOSFET, or FGMOS. These transistors have a gate that is electrically isolated from the rest of the structure. This isolation allows charge to accumulate on the gate and persist for decades, making flash memory a reliable choice for long-term data storage. Floating gates enable precise control of stored information in memory cells. SLC versus MLC. Flash memory comes in two main forms: single-level cell, SLC, and multi-level cell, MLC. SLC stores just one bit of data per cell. It offers faster speeds, greater durability, but lower storage density. MLC, on the other hand, can store multiple bits per cell, allowing for greater storage density, though at the cost of reduced speed and endurance. Logical gate equivalence. Interestingly, while flash memory cells are not physically made of NAND or NOR gates, their logical behavior during data read and write operations mimics these gates. In NAND flash, cells are connected in series, resembling a NAND gate configuration. In NOR flash, cells are connected in parallel, functioning similarly to NOR gates. This logical arrangement defines how data is read and written efficiently. Understanding these architectural foundations helps us appreciate how flash memory balances reliability, speed, and density, catering to a wide range of applications. There are two primary types of flash memory, NAND and NOR. NAND flash is known for its high storage density and cost-effectiveness, making it ideal for mass storage devices. On the other hand, NOR flash is recognized for its faster read speeds, making it suitable for applications requiring quick random access like BIOS chips and microcontrollers. As we proceed, we'll explore these types in more detail. Let's examine the architectures of NOR and NAND flash memory. Their unique designs are tailored to their specific uses in the digital world. NOR flash architecture. Starting with NOR flash, its memory cells are organized in a parallel architecture, which means each cell can be accessed independently. This design makes random access faster and more efficient, making it ideal for applications requiring quick read times, such as firmware storage in microcontrollers. NOR flash is frequently used in environments where precision and speed are crucial. NAND flash architecture. In contrast, NAND flash uses a serial architecture, where memory cells are connected in series. This configuration allows for higher storage density, making NAND more cost-effective. However, the trade-off is slower random access speeds. As a result, NAND flash is best suited for mass storage devices like USB drives and solid-state drives, where large storage capacity at a lower cost is prioritized. NOR's parallel design excels in speed and precision, while NAND's serial structure emphasizes storage efficiency. Each type has been optimized for specific applications, ensuring they meet diverse technological needs. Let's delve into the basic scheme of flash memory cells and explore how NAND and NOR architectures are designed to store data efficiently, whether it's a single bit, SLC, or multiple bits, MLC. At the core of flash memory is the floating gate MOSFET, a specialized transistor capable of storing electrical charge. This floating gate allows flash memory to retain data even when power is turned off. The data stored in a cell depends on the charge in the floating gate. In single-level cell SLC architecture, each cell stores a single bit of data represented by two charge states. In multi-level cell MLC architecture, each cell can store multiple bits by distinguishing between more charge states, increasing storage density. In NAND flash, the memory cells are connected in series along a bit line. The drain of one cell connects to the source of the next, forming a chain. The bit line is only activated when all word lines are high, which mimics the functionality of a NAND logic gate. This design minimizes the number of ground wires and bit lines, making NAND flash smaller, denser, and cheaper. It also supports advanced configurations like 3D stacking, where cells are layered vertically to further enhance storage capacity. However, since the cells are connected in series, accessing individual cells requires sequential operations, making random access slower. In contrast, NOR flash arranges its memory cells in parallel. Each cell is connected directly to a bit line at one end and to the source at the other. This design ensures that a memory cell stays high only when the bit line and word line are both low, imitating the behavior of a NOR logic gate. Because the cells are connected in parallel, NOR flash allows direct access to individual cells, making it faster for random access operations. However, this comes at a cost. The parallel configuration requires a larger silicon area, making NOR flash more expensive and less dense compared to NAND. NAND flash uses a NAND gate configuration for its memory cells. These cells are grouped into pages, and several pages make up a block. Data is accessed sequentially, which is why NAND flash has slower read speeds compared to NOR flash. However, this architecture allows for higher storage density, making it ideal for applications like SSDs and USB drives. Let's dive into the architecture of NAND flash memory, which is designed for high-density storage at low costs. Series connection of cells. In NAND architecture, memory cells are connected in series along a bit line. The drain of one MOSFET connects to the source of the next. The bit line only becomes active or low when all word lines are high, which mirrors the logical function of a NAND gate. Efficient design. This series connection minimizes the number of ground wires and bit lines required, making the design compact and cost-effective. Additionally, cells can be connected directly using a doped or conductive layer, enabling efficient signal transmission. Modern NAND flash takes this a step further with 3D vertical stacking, where multiple layers of memory cells are stacked on top of each other. This innovative approach significantly increases density without expanding the physical footprint. Advantages and limitations. The design of NAND flash offers several advantages. It's smaller in size, making it denser and cheaper compared to other architectures. However, there's a trade-off. Individual cells cannot be accessed directly. Instead, data access is handled in blocks, which can slow down certain operations. The NAND flash architecture strikes a balance between cost, density, and size, making it ideal for mass storage applications like USB drives and SSDs. NAND flash performs three main operations: read, write, and erase. During a read operation, data is accessed sequentially from the memory cells, which can be slower for random access. In a write operation, new data is programmed, but an entire block must be erased before writing. The erase operation happens at the block level, which can introduce latency. Despite these challenges, NAND flash's high storage capacity and cost-effectiveness make it a preferred choice for many applications. NAND flash is widely used in devices requiring large storage capacities. These include USB drives, memory cards, and SSDs, which offer faster access speeds compared to traditional hard drives. It's also found in embedded systems, powering devices like smartphones and cameras. Its ability to provide large storage at a reasonable cost is why it's so prevalent. Now, let's look at NOR flash architecture. Unlike NAND, NOR flash organizes its memory cells in a NOR gate configuration. This setup allows for parallel access to individual memory cells, resulting in faster random access speeds. NOR flash excels in applications where quick access to specific data is crucial, such as firmware storage in BIOS chips. Now let's explore NOR flash architecture, which is designed for quick and efficient data access. Parallel connection of cells. In NOR flash memory, cells are connected in parallel. Each cell has one end connected to the bit line and the other end to the source. This configuration ensures that a cell only stays high when both the bit line and the word line are low, mimicking the behavior of a NOR gate. This arrangement allows NOR flash to access memory cells directly. Key characteristics. Because of its parallel design, NOR flash supports direct access to individual cells, making it faster to read compared to NAND flash. This is particularly useful for applications requiring frequent and fast random access, such as firmware storage in microcontrollers. Advantages and limitations. NOR flash offers some clear advantages. Its parallel configuration enables quick access to individual memory cells, resulting in fast read speeds. However, there are limitations. NOR flash is more expensive than NAND because its design requires a larger silicon area for the same memory capacity. NOR flash excels in speed and accessibility, making it a great choice for applications requiring rapid random access despite its higher cost. NOR flash also performs read, write, and erase operations. However, it does so with distinct advantages. Read operations are fast and allow for direct random access to individual memory cells. Write operations can be performed on a per-byte basis, providing flexibility. Erase operations are typically at the byte or sector level, allowing for more precise modifications. These characteristics make NOR flash ideal for applications needing speed and reliability. NOR flash is used in applications where random access to data is essential. For instance, it's commonly found in microcontrollers, where firmware execution speed is critical. It's also a staple in BIOS chips, helping systems boot quickly. Additionally, NOR flash is employed in embedded systems for networking equipment and industrial control systems. Let's compare NAND and NOR flash memory. NAND offers higher storage density and cost efficiency, but slower read speeds and block-level erase operations. NOR, on the other hand, excels in random access and faster read-write speeds, but is more expensive and has lower storage density. Both NAND and NOR flash have their challenges as mentioned in the slide.